Welcome. In this lecture, we are going to show steps for FPGA implementation of digital voltage mode control in a buck converter. So, here we will say hardware setup prototype of a digitally controlled buck converter, step for FPGA implementation of digital voltage mode control and the live demonstration of load and reference transient performance. So, if you go for FPGA based digital voltage mode control implementation, we have discussed this in sufficient detail from lecture number 71 to 74. And then these are the PCB picture prototype that we are going to consider, and in this particular demonstration we are going to consider digital voltage mode control in a continuous conduction mode or a synchronous buck converter, and this PCB is for the buck converter, then signal conditioning circuit and the Xilinx FPGA that we are using FPGA prototype. And this is the picture of this our setup, where we are programming through computer, and this computer, that USB cable is connected, and the top part of here is a signal conditioning board, and you can see the bottom part which is the FPGA. So, signal conditioning board is just plug onto the FPGA, okay, and this is our power stage, and here this probe is used to measure the output voltage, and this current probe is used to measure the inductor current, and this is the power supply. You can see it is set V in to be 3.3 volt we are applying. Okay, there are two power supply, two supply. One is for the buffer, like op amp supply and all this, that is for supplying op amp, ADC, DAC and all, and we have used voltage regulator in the PCB also, and this particular one is used as the input to the DC-DC converter, which is this 2 point, okay, and this is your current probe, that thing, this is oscilloscope. So, here if we take a closer look, so again you can see the bottom one is the FPGA one and the top one is the signal conditioning board, and this is the USB cable that we are going to consider, and this is our power stage prototype, and this pin we are taking the output voltage. In fact, we can get the output voltage much cleaner if we can tap directly from the capacitor, output capacitor, but just for make it flexible for the demonstration we are using this one, and this is a current probe or 120 megahertz current probe, and you can see the input voltage is the first channel is the input voltage, which is 3.3 volt, and this one 10 volt for supplying to the op amp, ADC and so on. So, this digital control implementation, what we have kept, that means I just want to show you this board we have ADC and DAC, though for voltage mode control you do not need DAC, and these data are getting interface with the FPGA through this IO plug-in pin. So, this side also we have, and they are going to the FPGA IC. So, that means this IO pin ultimately whatever is going is nothing but this interface, and FPGA, inside FPGA we are implementing digital voltage mode control. Okay. So, this is the realization, and where we are using all the inside logic, and we have demonstrated all the Verilog codes and etc. And we have discussed in lecture number 57 that what are the steps for plugging this this computer, and then how to dump the code, how to compile the code, how to synthesize, then how to generate the programming file, and how to dump it into the actual FPGA. So, these steps are discussed in lecture 57. Here we are only recollecting with our code. So, it is a digital voltage mode control. So, you can see this is the main module which should be kept at the top module. So, this main module is calling sub module, which is a clock generator, then digital PID controller, then DPWM plus dead time circuit, and there is a user constraint file, because this file will link with the actual IO pin with their address, because we are taking the clock data 100 megahertz clock through this pin. We are sending the ADC clock from here, we are sending the DAC clock, though DAC is not required here. We are sending the high side gate signal, it is going to the driver. We are sending the low side gate signal. We are capturing the ADC data, which is 2s complement Q1.9. We are sending the DAC data. In this case, we are sending 0 data because we are not using DAC, but since the design is made, we are just making this in our module, but we can drop it. This is used for the load transient, that means the Q load is 1 means it will go for the load step up transient, Q load 0 means load step down transient. And this is to select the transient, there will be an external switch. If you set it one position, it will be load, if you set it another position, it will be reference transient. And all this code we have discussed in lecture I think 72 and 73. So, we are not going to discuss again. Here what we are going to show the top module. So, initially before going to actually implement, we have shown some case study of how to simulate, because in lecture number 80 I remember that I think lecture number 80, I think it is not 80, 70, I think lecture 70 we have discussed how to simulate a PWM block with gate signal and dead time. So, then we have to go to the simulation mode and we can check all the timing diagram. Once each blocks are simulated and tested, then you are ready to go for the implementation part. Once you go to implementation, we have to make sure which block is your top module, and then if you select top module, then these are the step, the synthesis step it will go, then implementation of the design, the synthesis will generate RTL, okay, and the implementation how this RTL, because Verilog is a platform independent, that means the same code can be used in a Synopsys and other digital tool to synthesize and in fact design one digital IC. But when it go to FPGA, so this step actually require this implementation stage is the critical. It will take that IC and reroute that FPGA pin, because FPGA we have discussed lookup table, configuration logic block, then programmable IO pin. So, all this interconnect of the implementation will be done in this implementation detail, and we have to be very careful about this what FPGA IC are using. So, we are using this particular part number of the FPGA of this package, this must be consistent, otherwise it will give you the wrong result, because this will link, it will take the library of the Xilinx IC and it will correspondingly take the library of the relevant IC, and then it will make the IO interconnection of this. Once it is done, then it will generate the program file, and we have discussed that we want to generate a .bin file, binary file, and this will be loaded in the using another software that we have discussed in lecture 57. So, this is the first step. If we show the whole code one by one, we are changing only this file, because there is a 4 these blocks. So, transient creation, these are calling clock generator, digital PID, DPWM, and finally, this is the end of the fourth one. It's the main module. So, it will be 4 by 4. Next, if you go to separately clock generator, you see this implementation will not come, because it is not the top module. But we have discussed the clock generation block. So, I am not going to discuss detail. This block we have presented in the lecture 73, even we have presented in I think 77 also for current mode control. So, these things we have discussed, but it is just showing the screenshot of the FPGA coding. Then we are going to talk about digital PID controller. These blocks are also discussed in our presentation, which was probably 72 and 73 we have discussed. 73 was digital PID controller. So, we discuss in detail, we are not going to discuss again. This is again a sub module of the main module. Then the DPWM dead time, this block we have discussed in the context in lecture number 70, where we have also simulated. That means, if you have a pulse width modulator and if you compare with a fixed reference, that will generate a duty ratio command, and that can be used to generate your high side and low side gate signal with suitable dead time, that also we have discussed. So, there is a redundant block, actually you are not using digital PSM. When you go to multi-mode, we will be using this block, but here dead time we have discussed about different code of dead time. In fact, we have discussed in detail in lecture number 72, the Verilog code. So, this part is over. Now, the most important part for the implementation, the user constraint file, and we have discussed in lecture number 57 that how to right click on this file and add this implementation. Okay. Then once this program generation is over, then what are we going to do? then we have to load to the target device, and that part we will be showing in the live demonstration how is it doing, and finally what is happening in the actual circuit. And this is a picture of the live demo, but now we are going to consider all the steps that we have discussed in a short live demonstration. So now we are going to demonstrate the digital voltage mode control experiment, which we have already presented in the class. So here we have already discussed in lecture number 91 that what are the steps for synthesizing. We have demonstrated all the Verilog code. Then we have told what are the steps, like first you have to synthesize, then implement, then design. So as if we have all the modules here, and you save file, dead time, digital PID controller, clock generator, and the main module. So we are first generating the program file, we will rerun it, and this is the Xilinx ISC software tool, and we have already discussed about what device we are using, everything in detail. Now you see one by one the stage is executing, like synthesis is over, then now it is going to implement. So synthesis will generate RTL logic, then implementation will actually try to map into the target FPGA device, the HDL code. That is over. Now once it is generated, it is generating the .bin file, which will be dumped into the FPGA. So now that stage is coming. So now we are going to, so this process once it is over, now we are going to this MIMAS FPGA configuration tool. We have already discussed the steps, and we are taking the file .bin file. So this is the voltage mode control file. You can see the .bin file. Once you select, it will show that it is selected .bin file. Now we are going to program. So that means it will selected file is DPWM_VMC.bin. Now it is programming. The bin file is getting programmed into this FPGA device. So it is dumping. Once it is dumped, the code is dumped, then it will verify once, and then there is a red light at the bottom, so it is not visible from here because it is in between two boards. The top board is our signal conditioning board, the bottom is FPGA. So FPGA has a red LED light which will display when this dumping is over. The LED light will actually stop. Now it is showing the program dumping process is going on. So now it will verify the process, that means whether it has been correctly dumped or not. So that is the final stage. Once it is over, then we will move to we will turn on the power supply. Now we are going to turn on the power supply. So first we will turn on the second supply, that is the powering for the signal conditioning circuit, then buffer circuit, IDC and all these, because we have LDO in the board which will derive all the required power supply from this 10 volt. Now we are turning on the main power supply, which is the input voltage of the buck converter, and as we have discussed, we are taking 3.3 volt as the input, but you can also increase the input voltage, there is no problem. Now we are going to first set based on the trigger. So I am just showing here the load transient response. In fact, the load transient response, we have not yet designed the compensator properly. We have chosen some value, but for the given value, this is the transient performance. And in the 11th week, we are going to design, first we need to validate how to realistically model our MATLAB model to closely match with experimental result, whether they are actually close or there is a deviating. We will also show the validation process, and there followed by that we will show the design step. But here imagine that we have somehow designed the controller and the controller values are already displayed, we have shown in the class. Now with that controller value we are making a load transient where the resistance initially it was connected, you can see 13.5 ohm resistance. Now this RSW, which is 0.33 ohm, that is connected in parallel here. As a result, you can see a load step up transient. So if we stop it, this is a step up transient where the load step is happening here. This is an undershoot, current overshoot, and then there is a overshoot due to the low step down transient. Now we also have, and we have discussed, we have shown this, we are going to show the results in more detail in the subsequent lecture. we also have a provision for changing to reference transient. So there is a switch, and we have discussed there is a switch called QLR, which will select the transient type. So when it is 0, that will take the reference transient. When it is 1 or vice versa, sorry, it is 0 means load transient, 1 means reference transient. So here we are showing the reference transient. So first it is stepping down, that means it was 1.1 volt, you can see 0.2 volt, 1, 2, 3, 4, 5. So this is 1 volt, this is 1.1 volt, then it is going down to 1 volt, then again it is going to 1.1 volt. So there is a periodically reference step transient which is happening from 1 volt to 1.1 volt and back to 1 volt and so on, and this is a response. So now we have shown that how to run this voltage mode control. Now if we increase the input voltage accordingly, you can check the waveform how it is getting affected, and we can design for various input voltage condition, and we will discuss about the design process in the subsequent lecture. Now we will move to the class. So now we have just concluded our live demonstration, and we want to summarize that we have discussed hardware setup, prototype, digitally controlled converter. We have shown step for FPGA implementation of digital voltage mode control, and we have also considered live demonstration of load and reference transient performance. That's it for today. Thank you very much.